session. So today I will try to connect the tutorial sessions to the theoretical part in the morning all the time. So we were talking about various approaches to computational design, and I'm not going to go through the basic ones. I would really like to show you, or maybe together we can figure out how can we do the emergent design using Grasshopper. And I will give you a set of tools. I will try to teach you the tools, and then maybe we can together somehow figure out how can we actually utilize these tools so that we bring real emergence within the design. This is, as I said at the very beginning, I really like to give you the complete set of tools and complete understanding without any gaps. We are not such a big group. Feel free to benefit from the fact, and whenever you are not completely sure what am I talking about, just interrupt me and we'll go through the whole thing in high detail so that you actually get all the information that you need. All right. Okay, so today we will use iterative methods, and I will try to explain what the iterative methods actually are. With Grasshopper, the way Grasshopper is designed, mostly what you do is you do it in one go. So you get some inputs, then you have some constants. Like inputs are something that you reference from Rhino to Grasshopper. So for example, I draw a circle, then I reference the circle as a curve, like this. So the curve is here, and I can do something with it. I can move the curve, for example, in the Z direction, and I can use a slider that defines how much am I moving stuff. So, right? So this is the basic thing. These are the inputs referenced from somewhere, usually from Rhino viewport, but you can also reference stuff from files or just read it from different sources. And then there are constants. This is something that is constant, and then you execute in one go. So this is executed, and then there is a result. The good thing about Grasshopper is that it actually allows you to process larger amounts of data. That's the whole point. So instead of just working with one curve, I will just let's work with one curve, but instead of moving it along one vector, which is this Z vector, I'm moving the circle upwards. I can have more Z vectors, and I'll do it, for example, like this. And just by changing some constants, in this case, it's going to be just one last check if we are streaming properly. Yes, we are. Okay. So like this. Okay. So just by changing the number of numbers that the series is generating, I'm actually doing the same stuff with more data. And this looks like something that is repetitive. If you are programming in other programming languages other than Grasshopper and other than functional programming languages, we'll discuss this on the last day. Grasshopper is a very special kind of a language because it combines two things, two paradigms. One is the visual programming because it's a node-based visual programming language, and that it's a functional programming language, which is a very powerful, beautiful, and nice thing, but still very exotic. Actually, not really. Still, this is the oldest way of programming, and it's much better than what most programming languages do. But it's also kind of difficult to use and difficult to optimize for performance. But anyway, this was a detour. What I was trying to say is that if you ever programmed in anything else, like processing, for example, the way you would produce so many circles like this is by using loops or repetitions. In fact, you would just take a circle, then move it, then repeat the action, take the circle and move it along a longer vector, or take the previous one and move it a little bit, take that one and move it a little bit, and so on. And you would create 27 circles like I did. In Grasshopper, it's different. You're not repeating actually the action, the imperative procedure, but you are repeating data. So in fact, what is happening here, it's not the move that is repeating, it's the data that is more than one piece. We've got 27 pieces of data. Here it's numbers, here it's vectors. And then we are applying one set of data, which is the circle, to another set of data, which is the z vectors. And then Grasshopper automatically applies one on another. The way it does it is called longest list data matching, and I made a tutorial on that. But the important notion here is that what is repeated here is the data, it's not the action itself. This is quite useful for a lot of applications. The nice implication about that is that this only happens once. So what you see here is this is executed once. So the circle is referenced once, then the series of numbers is just generated once, then the z vectors, different lengths, are generated once, and then all of them are applied to the circle once. And the result is a list of values. What you would do in a different programming language other than Grasshopper is something like this. Instead of repeating the data, I will just disable this so that we don't really see the result. In processing, for example, you would very probably do something that looks like this or equivalent of this. So here I'm repeating the action like this. And I would have to do this 27 times to actually achieve the same result like I did before. So you see the difference. Instead of repeating actions, I'm repeating data in Grasshopper. The good thing is that even the number of repetitions can be controlled using a slider, which means a constant. In processing, you would have something that is called a for loop or while loop, and you will repeat the same loop 27 times to achieve that. And you can also change the parameters there. But still, the logic behind is that this is the action that I need to repeat over and over again. In Grasshopper, in most cases, when you are manipulating geometry, you don't really have to think about repeating the action. Like here, for example, it really doesn't make sense to repeat the move many times. Just like when you are doing some sort of paneling, we can have a look. When you have I don't know, I'm going to just draw some surface like this one, rebuild, 4, good, and like this. All right, I just want to make a curved surface like this, and then you can I will reference it to Grasshopper surface, just like that. Okay, then yeah, I just forgot how is that called. I want to populate the surface with points, surface points maybe. No, this is just the control points. Yeah, it will be divide surface. Yeah, I think so. Okay, yeah, that works for me. So I divided the surface into several points, and it gives me a plane, which is this one, and then I can draw circles on the plane. Oh, sorry. Like this. Okay, this is normal. Yeah, well, I need to generate a plane. I will explain just in a bit when I'm happy with the result. Okay. So now I populated the surface with some circles. They are oriented well, which is already some parameter that I made. And also I can change the size of the of the circles based on, I don't know, the z coordinate. Yep, this. Just give me a moment, and I will explain everything in depth. Map numbers, which is z, from here to this is this, and this is the radius. Okay. Right. So here, what am I doing? You see that there is an input surface. Then I divide the surface. It's called dividing surface, but basically it just populates the surface with some points. The points are equal distributed along the u and v direction of the surface, the local coordinates of the surface. Then when you do that, the component doesn't only tell you the position of those points, but also the normal vector, which is a vector perpendicular to the surface. We can visualize that, which is here, like that. This is the position, this is the vector, and you see the vectors, they're showing direction perpendicular to the surface. I created planes that are oriented along the normal vector. So there are planes that are tangent to the surface. And then I'm drawing circles on those planes. Sorry, okay, that's good. So I'm drawing circles on those planes. That makes the orientation of the circle. So the circle is tangent to the surface. And also I'm changing the radius of the circle based on its z position. In other words, based on where it is in the vertical direction. The way I do it is like this. I'm deconstructing all of the points. Deconstructing points means that I'm getting the numerical values for each of these coordinates. So this would be all the x coordinates, this is all the y coordinates, this is all the z coordinates, that's the one that I care about. So for each point, I've got a separate z value. This component is called bounds. It actually takes a bunch of numerical values, bunch of numbers, and it creates a domain which contains all the numbers. Basically, it finds the smallest and the largest number, and it creates a domain from the smallest to the largest number. And this is basically, it tells me that all the z coordinates of these points are between these two values, and we can see that. So all the z coordinates are between -9 to plus 4.3, and so on. And I'm remapping. Remapping is recalculating the numbers. Similarly, so from this domain, I'm remapping the numbers to a domain 0.5 to 2.5. In other words, point that was on the bottom here will generate or trigger recalculation of a value 0.5, and the point here will be associated with value 2.5, which I will use as a radius for a circle, which means that the circles on the top are bigger than the circles on the bottom. We can even check that even more. I will just make this surface a little bit more curved, and you see that the circles on the bottom are really small, the circles on the top are really big. So even though I'm now manipulating 121 circles, a lot of values, a lot of geometry with a lot of values like orientation planes, radius values, still I do everything in one go. Unlike in processing, for example, where I would need to go circle by circle and just setting the value one by one. Is this clear so far? I hope so. I don't really have any feedback from, yeah, I do a lot of feedback I do have. Let me see. Clear? Yes, good. Okay, happy. Yeah. Now I will show you an example where I'm actually not really able to use this logic. When I was talking a long time ago to David Rutten, he told me that you can basically do everything with Grasshopper and you don't need to implement any loops there. I was missing it a lot, but well, you can do a lot of stuff without loops, but there is stuff that you cannot do without loops. And it actually opens a whole new world of design. And I will show you a good example where I cannot imagine how to actually do that. Well, I can imagine how to do that thing without loops, but it's incredibly complicated. Let me explain to you now without Grasshopper, just in pure Rhino. So imagine this logic. You have a point somewhere, like here, and then you want to move, really copy the point in any of the 4 directions, like left, right, front, back, or basically in any direction. Let's do it completely freeform. I want to move it 1 unit in any direction, random. Then I want, from that point, I want to move in any other direction, again random, and then again random direction, random direction, random direction, and so on. The problem is that with the basic tools in Grasshopper, this is almost impossible. Like, this example is still possible to do, but there are other examples that are impossible to do. The reason is that these are temporal steps. These are steps in time. So at the beginning, you know the position of the original point, but then there is a second point that is based on that position here, and it's actually moved by a random value. But this one is based on the position of this one, and it doesn't exist at the very beginning. So if I try to apply the same logic I did before, like here, to do everything at once, let's try to do it here. I will just construct the first point, construct point. So this actually creates a point here at the world origin, and then I move it, and I will generate a random vector, which I will do like random, 3 random values, like that. It's funny that there is no random vector component in Grasshopper. Wait, like this. So in fact, I made one. So there is like random vector in my Boyd plugin, but let's not use that one. So here I created a random vector showing any random direction. It's a positive one, so I need to change the domain from -1 to 1, like this. Also, I will make sure it's a unit vector, which means that the length of the vector is 1. So now it's pointing some random direction, and I can use this vector to move the point to some new location. But if I apply the same logic that I do everything in one go, I can generate a lot of vectors like this. I can do it this way. Let me show you. This is a random seed. So I will just set the seed to something else. And you see when I change the seed, it actually moves the second point somewhere in a different location. But if I insert more random seeds, so like, for example, I will generate 5 random seeds. I believe that this actually generates 5 separate vectors. Yes, 5 random vectors, and you see that it actually moved, it created 5 new points because I moved it 5 times. Now the thing is that, actually let's not do it 3-dimensional. I will just make it 2-dimensional, and yeah. For the moment, it's easier to see. Now it's all happening on a flat plane. So I generated 5 vectors it doesn't matter that it's a data tree. I will just flatten it down now because it doesn't matter. It doesn't make any difference. The problem here is that I do have 5 vectors, but I'm always using them to move the original point, this one. So anytime I move it, what actually happens is this, that I will move the original vector to its new location like this. So instead of doing a path like I planned here, I planned to do something like this, I did this because I always take the first one and move it. And only then I can move it again and again and again. So with Grasshopper as it is, to actually achieve this path, I would have to do something like this. I need to generate only one vector. I will just make a slider for the random seed because I want to randomize it differently in each step. So this is the first step of moving the point. I will disable this one so that we can actually see it better. So I moved it here. Then I have to do the same thing again. So this was the original point, and then I will copy paste the entire logic, the action, and I will have to move this one and create a line from here. And when I change this random seed, it will just go some other direction. And then I move it again like this. No, sorry. Yes, sorry. Like this. And again, I can change this random value, random seed, and so on. And if I want to make a path that is 100 steps long, I will have to repeat the logic 100 times. And this is something that you barely can do with a pure Grasshopper, with a vanilla Grasshopper. You need to have something that allows you to use loops. And it's not built into Grasshopper, unfortunately, and you need to use a plugin. And there are several. Is this problem understandable to you? Is this clear? What the problem is? Okay, good. So, in fact, if we have enough time, I can show you how to do this with vanilla Grasshopper. It is possible, but it's a crazy logic. But yeah, it's doable, even without the plugins. But there are other things that are certainly not doable. The conceptual problem here is that we need to use unexisting data as an input to another step of the same logic. Because when we are generating this point, we need this one to exist. And because this one doesn't exist at the very beginning, we cannot generate this one. So instead of copying the logic over and over again, I need to repeat it in a more sophisticated way. And that's where Anemone comes in. Actually, Anemone is not the first looping plugin that I noticed for Grasshopper. There was a plugin called Hoopsnake before, but I actually didn't really like the way it looked. Although, in a way, it was nice. But I prefer this Anemone that is made by Mateusz Wierzycki. For some people, for some reason, people think that I made it because I'm using it so much in promoting, but in fact, I didn't. I really have, no, I don't have the Grasshopper skills to actually develop a plugin like this. So this is made by Mateusz. Mateusz actually made a lot of very interesting plugins, not only Anemone, but also Starling, which was one of the first plugins that he made. This is for mesh analysis. Then he was somehow involved in the Lunchbox plugin, I think, or maybe not really a Lunchbox, but one of them. Like that one. Also, he made something called the Squid, which is an incredibly useful plugin for drawing. Then he also did something for the point cloud processing. I forgot the name of that one. And also he made OWL for the neural networks, and I believe a lot of other things as well. But actually, to be honest, I'm only using this one. Well, the good thing about his plugins is that they really bring functionality that was not really available for in the vanilla Grasshopper. It was not there. So whatever he made is something that actually is incredibly useful. So anyway, let's go back, and I will just show you how can we use Anemone to actually achieve this thing. I will copy paste this again because I don't really like this thing. I will just freeze it. Okay, so we've got some point at the beginning, and then we move it along some random vector. And then what we want to do is we want to use this generated point as then input into the same logic over and over and over again. So we want to actually repeat this. So whatever comes into this move as an input, then it comes as an output, and we want to bring it back as an input again and again and again and again. As many times as many steps we want to make. So for that, Anemone has two components. One is called loop start. The other one is called loop end. And basically you can imagine this as some brackets, and whatever you put into these brackets, into the two brackets, is being repeated over and over again. But it's done in a very smart way because everything is triggered by data. Just like Grasshopper in general is based on data processing, this again, it is repeating the logic, but it's repeating it based on the data. Let me explain what the components actually do. You need to connect them first with these two, which actually tells them that they belong to each other. That's very important. Now, whatever is in between of them is being repeated, and it's repeated this way. You say how many times, that's the n input. So I say I want to repeat 10 times, like this. Then the t input is a trigger. Whenever something comes into the trigger, then this restarts. In fact, it's not really that much needed, and actually it was me who wanted it there. There's a question like fractals, when something repeats. Fractals, let's go back to fractals after I explain this, but yes, you can do fractals with this as well. Anyway, so the T input is a trigger to restart this loop. But it's actually not necessary, because whenever you input new data into any other inputs, it restarts anyway. So just like any other Grasshopper component, let me just show you what do I mean. So when you draw a circle, and I will make a slider. So there is the number slider here, and the way this execution actually works is that Grasshopper is now doing nothing. It's calculated and doesn't have to do any new things. But when I move the slider, it actually generates new data here, and it triggers this one to recalculate, recompute. Because my computer is fast, and this is a super simple Grasshopper definition, this happens almost instantly. But in fact, the recalculation of this one is being triggered by the change here. So whenever I send new data here, this is being recalculated. Otherwise, it's not being recalculated. The same applies here. So whenever I plug anything new here, this is going to be recalculated. So what do I insert here? You see that there is D0, 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 D0. You can imagine this as a data dam or data flow. You insert the initial version of the data. In our case, it's the first point of the path. Then it comes out of here, and you can use it to move the point. I will just take this line away because that's just for visualization purposes. So I will put this here, and then this comes out. I move the point, and then I plug it back in. So the new version of the point comes back in, and then it's being returned here. And just like that, the new version comes out of here, and this is being recalculated because the move gets new input and it's recalculated. It outputs the new one, and it comes back and over and over and over again 10 times. So what happened actually is that the first original point, which was this one, was moved along a fixed vector, one vector, 10 times, which means that the result is here. This is the resulting point, because it changed, moved, and so on. This is not very useful because we don't see the process in between. To do that, to see the entire path, I can right-click here and say record data. Then I double-click here at the loop start. I double-click, and you see that it actually recorded all steps of the point when it was moving. So this was repeated many times, but each time something entered the D0 here, it's being recorded here, and recorded actually means that in the output here, so when this loop is over, in the output, there is 11 versions of the data, or 11 actually 11 branches of a data tree. Each one has recorded the historical version of D0 in each repetition, which is actually called iteration. So this is the D0 after the first repetition, first iteration. This is D0 after the second iteration, third, and so on. Here, this is a data tree. Just to simplify things, I will just flatten. Oh, I'm just making a lot of typos. I will flatten this tree and just for simplification. So now I've got them in one simple list, and I can draw a polyline like that, and it actually draws the path. Now, you might ask why the path is a straight line. Do you actually know why the path is a straight line? Shall I ask you? Any idea? Nope. The thing is that I'm generating a random vector, but the random vector is the same for every repetition, every iteration. There is no new vector being generated for each repetition. And to do that, I need to change the random seed for each repetition. And the easiest thing to do is just to use the counter, the repetition counter. This is a number that changes each time, like for a repetition number 1, this is 1, for repetition for iteration number 2, it's 2, and so on. So if I use this as a random seed, it means that a new set of random numbers is being generated in each iteration. And it means that each step is going to be different than the previous one. Let me restart again, and you see that it actually did something. So now the path is actually randomized, so it moves in a random fashion. I can actually change the number of repetitions to more than 10. I will just make 100 so that you see that it doesn't really matter how many repetitions do I want to make. If I had to copy the logic all the time, this would be like 100 times this, and that would be crazy. And I wouldn't be able to change the numbers the way I want. Is this clear? Is this understandable? Yeah. Okay. Also this is kind of messy because now the vector is completely random, and it doesn't really know anything about the previous vector. So if you just want to do something that is like this, you can apply some sort of, let's call it an inertia. Basically, that means that you when you move in one step in this direction, you only want to change the direction a little in the next step. Here, now it's changing completely randomly. The next step could be anything, just like this. So we can actually adjust that as well. And I'm only showing you because I want to show you other options of Anemone. Let's just, again, freeze this one, and let's update this one a little bit more. So what you can see here is that we have D0, D0, and so on. So this is data 0. But if I zoom in, I can add more data here. So I can loop and repeat. This is the fallback data. I can use more sets of data. So now I'm not only having the point itself, but I'm having also one more piece of data, and that piece of data will be the previous vector that we used. So in fact, I will only generate, I don't really need to keep this one here like that. So I will generate the random vector only once at the very beginning. Let's just set some random seed like this one. Now this is the vector, and I use that vector to move the point, and then for the next step, let's use the same vector. I will restart now, and it should actually work. The problem would be that now it's a straight line again, so it doesn't really change the vector between the iterations. But instead of generating a whole new motion vector for each repetition, I will just modify slightly the existing one. So I will rotate vector, rotate vector. So it's this vector because we are working in a flat on a flat surface on XY plane. I will use Z as an axis, Z vector as an axis, and the angle can be something random. And because I know that I don't want it to move way too much, I will go between 45 degrees plus and minus. So let's say negative, but the Grasshopper always works in radians, so I will just convert it into radians first. So now I have this, I think this is quarter pi. Yep. And I will create a domain, construct domain minus plus. So now I will generate a random number between minus 7.8, minus 0.78 and plus 0.78. So this is the random domain. This is the random seed, so that we have a different random number for each repetition. And then this is the angle that we are rotating the original vector, and we are moving the point along this slightly modified vector, and we also want to return the slightly modified vector to the loop end, so that in the next repetition we are modifying the already modified vector from before. Now let me restart, and you see that now it moves kind of smoothly, right? And I can set the number of repetitions to something more like 500. So it continues. Is this understandable? Is it clear? Okay, I hope so. So this is 500 repetitions. You might notice, actually, I will save this and I will send you the file afterwards. Like this. Yeah. Okay. All right. So, so you probably have noticed that this is not completely random, and you can see patterns there. The thing is that the random function within computers in general is not really random, and it's actually quite regular in a way. And it manifests because there is no, like in computer, there is no way of electrically generate a random number. The computer usually takes the current time and does some math to take the current time to actually generate using the math to generate some numbers. The time is the random seed. But if what happens here is that the random seeds are coming one after another, so it's a consecutive line of numbers starting from 0, 1, 2, 3, 4, 5, and so on. So if you generate random numbers and using non-random seeds, a sequence of non-random seeds, the resulting numbers are also not very random. They are going to be kind of, they will create patterns like this. So the thing is that if you want to randomize this properly, you actually cannot use consecutive numbers as random seeds, which is in fact not possible, because where would you get a random number? So my strategy here is to randomize as much as I can, although I know that nothing is completely random. I will just move this away. So I will never get a full randomness. Actually, if you, for some programmers who actually need to have very random numbers, they actually buy a new piece of hardware that is basically just measuring temperature and I don't know what to actually generate randomness, but we cannot use it here with Grasshopper. But for some specific cases, it's important to achieve a more random numbers than the usual computer actually allows you. Here, what I'm doing is that I actually take another random. So I'm using the same pattern of the consecutive numbers to actually generate a large set of numbers. So now first I will generate a random seed, and then I will use the random seed. So now I'm doubling the randomization, which is still not completely random, but it's much better than it was before. So when I restart it now, you will see that it will look way more random than it did before. And for me, this usually is enough. This, I cannot really see a pattern here. Yeah. I don't think there is one. Well, actually there is, but probably we would have to have a million of points to actually see the pattern. We don't see the pattern here, really. Good? Understandable? I hope so. Good. So this is the very basic stuff. Maybe you've known that before. Just let me know if you've seen this before. So this is something that I've got 500 repetitions. I wouldn't be able to do that otherwise. It's something that yeah, I wouldn't be able to do without having having a loop in Grasshopper. Well, actually, I would. This is possible, but let's do something that I cannot imagine that that would be possible without having a loop available. Let's start a new document, and when you look into the lineup for today, I just wanted to show you Anemone. In the next step, I will show you some iterative design. In fact, it happened to us before that people were asking, what do you do at the research? What are the outputs? So we just put together a website where we just uploaded all sorts of images that we could find. This is something that I could be showing also. I could have shown that in the morning sessions, and maybe I can show this stuff again tomorrow. For example, this is the weaving effector for the Kuka that we used in Tuscany that I mentioned. This is light painting with the robot. We were just we had long exposure, and we were drawing with an LED light attached to the robot. And this is hot wire cutting and all the other stuff. But for today, I would like to show you we can actually do any of these. Actually, even this one is made with Anemone. This is some growth simulation. It actually is not. It's not a little human or humanoid thing walking. These are not legs. Actually, what it is, it's this is a 3D print of that thing, and you see it doesn't really look like a walking thing. That just randomly happened that it grew, the mesh grew this way. But anyway, it looks funny, so I kept it. This one, for example, is a simulation of a game of life, which we are also not really going to do today. But you know, the game of life by Conway, who unfortunately passed away during this COVID crisis. The game of life is a cellular automaton. Basically, it means that it's a simple game with simple rules that actually generate some pattern results. It actually looks like a simulation of some behavior, and this is the game of life implemented in Grasshopper with Anemone, and each section, horizontal section, is one time step of the game of life, and it generated something, and then I connected the lines and the points into lines, and it created something like this. This is also some growth using Anemone, so maybe we can also do this. Let me know if you're interested in this one. This is already done in processing, but again, it's some sort of iterative growth. It's basically based on the idea that you already have some geometry, in this case, some points, and there is something floating around, sometimes gravitating to existing geometry. And again, you wouldn't be able to do that in one step. You need to do it in time steps. So the order in which you attach more and more things to the whole structure, it actually matters. And so on. This is the very first output that I did with my Boyd library. This is the path that was generated for the ring that I was showing in the morning. This is also some growth that is iterative. It looks like an ear, but actually it's some growth. To be honest, I forgot how did I do it. This one, for example, is the same growth like this one. If you put this into 3D, then something like this happens. Something like this happens. This is again the ring in rendered differently. And this is a simulation of a swarm simulation. We are going to do that today as well. But what I wanted to show you and do as a first thing is this. This might not really look like much, but actually there is, I really like this one a lot because it shows the iterative approach at its simplest. This is no simulation of any behavior, but it's a very simple thing where there are, at the beginning, there are some curves. Basically, it's this curve here and probably this curve here. Whatever looks like a large shape, large curve, was at the beginning. And then I was putting one stick after another. And the point was to put the stick on existing sticks or the original curves. And you couldn't really put it anywhere else. But logically, you cannot put the fifth stick before the fourth stick. And, there has to be this first one, and then you can put the second one, and only then you can put the third one, and so on. They need to exist at the time when you are putting them on. So let's do this. I actually think I've got another rendering of this one, but probably not here. But never mind. Maybe no. So let's do this thing. I've done this like 6 years ago, and I don't know exactly how did I do it, but let me just improvise here. All clear, all good? Anything you would like to? Oh, it's so nice. These 3D images becoming 2D images becoming 3D in Grasshopper. We can actually do that. Seems like a bird's nest facade in Beijing. This one, yeah, but this, I think the logic here is very different than the bird's nest. The bird's nest is basically just some chops of the original shape, and this one is like really adding one after another. But the real bird's nest, like the real animal bird nest, is being done this way. The animals, the birds, they bring the twigs and they put the twigs one after another. This is exactly what the birds are doing. So let's do that in Grasshopper, right? So I will just now create the first curves, and I will, if you want to or can, just follow me, and if you want me to go faster or slower, just let me know. Also, I'm wondering if you are really following me, if you are doing the same like I'm doing, because when we do the live workshops, people are usually following. So I'm wondering. I'm just modifying this like this one, putting this one here. Don't get scared. It seems like somebody is coming here. I think it's my colleague. So probably she will join us in real life. So we'll have a company. Okay, and let's draw a straight line here, like this. Like this. Okay. All right. Okay, so we've got some initial setup. I will put it here. This will have one very tricky part, and I forgot how did I actually resolve the tricky part in the original design, but let's just give it a try. Maybe you will figure it out yourself that something is not easy here. So, okay. So now I've got 3 curves, and I want to identify 2 points. I want to set 2 random points on these 3 curves, and I want to create a new line connecting those 2 points. The question is if you can get this document after the class. Yes, you will get the document, and I think I will just I think I will send it over an email, but let's see. Anyway, so the thing is that we've got 3 curves and we only need to have 2 points. So I think the easiest strategy now would be to generate more points and only pick 2 random points. So another strategy would be to first pick 2 lines or 2 curves and then generate 2 random points. I think that the second strategy is nicer. So now let's just pick 2 of the curves. So I think the easiest way would be to random reduce. The randomness here is kind of important. So random reduce basically takes a list of any data, and it will remove certain number of data. So I know that we actually need to have 2 pieces of curves. Right now we've got 3, so I know that I can take this list and remove exactly 1. So I can remove 1 and 2. Oh, what's wrong? It's 4 curves. Why is it 4 curves? Ah, because this one is twice there. Okay, now set multiple. So there are 3 curves, removing 1, only 2 remain, but this is not very systematic. As I said in the morning, when you are working with the computational design, you need to make sure that your algorithm, that is basically the device for creating the shape and form, you need to make sure that your algorithm is can work with any input data. So you need to make sure that this works also for a different number of curves, where the minimum should be 2, of course, because that's the logic, but maybe there's 100 curves. So instead of subtracting 1, I will just check how many curves we already have. I will check the list length, and I will remove 2, subtract number 2. So now it's 3 minus 2 equals, I need to reduce 1. So if this was 100, then this number would be 88 and 98, sorry, and this random reduce will remove 98 curves, and only 2 will remain, and those 2 will be random. We need to place here some random seed so that it's not always the same one. So I will just put a slider there, and then I will remove the slider and replace it with something more sophisticated. So I've got two lines now, or two curves. Also, let's make sure that they are reparameterized. The reparameterization actually means that each curve has its own domain, which means like a local coordinate. So you can say that the beginning of the curve has a value of 0, in the middle it's 0.5, and at the end it's number 1. And that's the local coordinate. But some of the curves, they don't need to have a domain from 0 to 1. They could have a domain from 100 to 1024, or something completely random. That can happen when you are trimming something in Rhino, or just doing some modification to the original curve. So we cannot be sure whether the curves are in the domain of 0 and 1. We need to know that because we need to know that at the beginning there is 0, in the middle there is 0.5, and at the end is 1. It is 1, because if we are looking for a random point on the curve, we need to know, we need to request the random number within certain domain. It actually would be possible to measure the domain, but the easiest thing would be to reparameterize the curves. Reparameterizing means that it actually recalculates the curve so that it actually is within the domain of 0 and 1. So now we are sure that the green curves are in the domain of 0 and 1, and then we can request random points on the curve. This is called actually evaluate curve. Evaluate curve. That's a component. You input a curve, and then you say that you want to evaluate a curve at a certain parameter. We know that it can be anything between 0 and 1. So let's put a number slider, and you can see that it actually gives us points at the beginning or at the end of the curve. That we need to get a random number. Oh, somebody's requesting bifocals. I'm not using those, but yeah, I can install bifocals, sure. Bifocals, actually, while I'm doing that, I would like to explain why this will be super hard for me to use, though. Yeah. I'm always using Grasshopper with the names of the components, because there is a good reason for that. Let me show you. So if you draw icons instead of the names, let me just do this. Okay. So when you see somewhere on the Grasshopper forum a definition like this, how the hell would you know what this is? It doesn't tell you. It doesn't. There is no clue. How can you actually know what this is? Whereas if you display the names, you can say you can try to type this name, and it probably will look it up for you. But whereas if there's just the icon, there's no way of knowing what the component is. So for me, it's unreadable when I just see the pictures. I just completely skip all the time. When I see just the pictures, the icons, I completely skip because it doesn't really make any sense to me. So, but anyway, some people I know, some people are used to use the icons. So I will use bifocals, which is just a plugin that gives you the name up here and also displays the icons. For me, this is going to be a huge pain because I cannot really, well, this will be difficult. But anyway, let's use it like this. Good. Okay. Now, yeah, I'm reading the chat. What do seeds in reduce represent for? The seed, okay. Any randomness in computer, just like I was explaining before, is always based on some data. And when you use processing or any programming language, when you call random, it gives you a random, different random number each time. And it is because it's based on, for example, current time. So it takes the current time as a seed, and the seed is you can imagine the random component. The random number generator is a very, very sophisticated mathematical formula that takes one number and gives you a different random number. So the seed is the random number trigger, and it's very useful in Grasshopper that you can define the random seed, because whenever you open a Grasshopper definition with the same random seed, you will get the same random number. And with the random reduce, it randomly removes certain items from a list, and the seed actually tells you it makes a decision which ones it is removing based on the seed. So with the same seed, you will get the same result all the time on all computers. That's the random seed. When you change the random seed, it will select different two pieces. Okay. So back to the, we have a discussion here about the icons and numbers. I'm always arguing with Alessio Arioli about the icons and the names. I'm always for the names. He's always for the icons. I think it's really a personal choice. Some people are more visual. Some people are okay with the text. I'm very okay with the text. Now, if you are just starting with Grasshopper, I really recommend using just the text names. If not, then just maybe use the bifocals. That's also a solution, but it looks kind of messy afterwards. We can also display full names here. If you display the full names, it actually the input and output pins, they get like a full description so that you know what they stand for. So we can do it like this. This is like a very, very basic setup. Is that okay? No, I'm not. The command is, if I want, I can close bifocals. No. That's okay. It's just I really do prefer the names. So anyway, let's do it this way. I think we cannot be more accessible than this one. This one should satisfy everybody, or dissatisfy. Whichever you prefer. Anyway, let's go back. We were identifying two random points on these two curves. We know that the domain of the curves is from 0 to 1. Let me take a sip of water, and then we'll continue. So we know that the parameter here should be something between 0 and 1. We can generate a random number. We basically need to have two of them. So the range here by default is 0 to 1, which is good. We need to have two random numbers. They are going to be different, because for each curve we need a different random number. Otherwise, if they would be the same, we would find a point here and a point here and then a point here and here. They would be very close to each other. So anyway, and we also need to have some random seed, which I also want to be able to change. So these are the random seeds, and I will keep changing these later on. They're different. Now I've got two numbers here. Okay, like this. So it actually selected 2 points here. One is here, one is here. That's cool. And let's draw a line between them. We can then make this a little bit more sophisticated. Actually, a line is, let's do a trick. Instead of drawing a line, let's draw a polyline. The reason is that with a line, you need to define separately the start point and end point. And we don't really have that yet, because here we've got a list of 2 points. And the polyline, it actually accepts a list of points, and it creates a line, a polyline between those points. If we only have if we only have 2 points, it creates a simple line. So I can plug this in and it actually works, and I don't have to decompose this. So I'm drawing a polyline between these 2 points, and it actually generated a line like this. And now I want to repeat this logic over and over again, like 500 times. So instead of just copy pasting the whole thing over and over again, I know that the logic that I need to repeat is this, and I can use Anemone to actually repeat the logic. I will save this. This is file day 1, file 2. The thing is that whenever you are using Anemone, your Rhino and Grasshopper can easily crash. Like, because you force it to repeat something over and over again. It's like with data trees, it happens so often that when you plug in something in a wrong way, then it crashes. So actually, I already have this instinct that whenever I'm placing the Anemone components here, I save before I do, because I might lose all my work. So yeah, it's a smart thing to do. So I placed Anemone here, loop start and loop end. And what do I actually want is that this is the original data, these 3 curves. Then I do something, and at the end, I have these 3 curves plus 1 new. So actually, I've got 4 curves. So before I plug it into Anemone, I will just generate the loopback data, which will be I will merge these original curves and the new curve into a new list that contains the original ones and the new one. As a result, unfortunately, there is a data tree. That's because of peculiarities of Grasshopper. The thing is that, I don't know if you're familiar with data trees, and that's a bit of an advanced concept here, but I said I'm never doing this. I said I never say just keep it as it is. But here I will do that because I don't want to go into data trees really. The thing is that the data tree is a hierarchical structure of data. So you don't only have a list, but you have lists of lists. And Grasshopper is actually creating data trees whenever it possibly can. So there are some components that in some cases could generate a data tree. So if that component has a chance to generate a data tree, it does it anyway, even if it's not necessary. So in other words, creating a tree is called grafting. So whenever a component could possibly graft, it always does graft. So what happened here is that the original data that we have here, they are in a data tree path 0. But the data that we generated here, the polyline, is in a path 0, 0, because somewhere along the line, somewhere, I actually believe that it's the random. So it happens that, yeah, it's the random that generated this path, because this random reduce could possibly create a data tree. So it did create the data tree, even though it only has 1 branch. Let's see. Oh, it even happened here. So it's probably the subtraction that generates the data. No. It's only here. It's a random reduce that possibly could graft, so it did graft. And when we merge here, we are merging something that is in the path 0 with something that is in the path 0, 0, which are different paths. So eventually this creates a data tree instead of a flat list. And the solution here is either flattening here or flattening here. I prefer doing it here because that makes sure that the order remains. So I have flattened the input here so that I make sure that it has a path 0. And here I flattened again. So again, I made sure it's got the same path, which is 0. And as a result, I have the 3 original curves and the 1 newly created curve at the end of the list. So like this, which looks awesome because instead of 3 curves in a list, now I've got 4 curves in a list, which is something that I wanted, and I want to keep repeating this. So in the next step, I could also randomly pick the newly created one, not only the 3 original ones, and I could put another random line somewhere here and here, which wouldn't be possible before because this one didn't exist. So let's loop this. So the loopback data that we have is the list of the curves. So the original when you hold Control Shift, you replug all the wires. So I will replug all the wires here. The original, the initial data are these 3 referenced curves. Now, all these 3 referenced curves, they come here. We do whatever we did here, and then we generated a new list of 4 curves, and that's the loopback data. And I will just plug this here. And in the next step, this one will contain already the 4 curves, and this generates a new 5th curve and the 6th curve and so on. But before we go on, I need to generate new random seeds for each repetition. In fact, we wouldn't see any pattern or repetition here because we are now choosing from the list is going to be longer and longer each time. So we will pick different curves each time, I believe, but still, let's generate new random seeds, but we need 2 of them. So I will take the random component, generate 2 random numbers from a very large range, something like this. So actually, I will explain one more thing here. Generally, this generates 2 random numbers. I will take the first one, list item. I will take the first one, I zoom in. This is the first item, this is the second item. I will use the first random number as a seed here, the second random number as a seed here. So I've got 2 random seeds, and this one will have the counter as a seed. So for each repetition, we will generate 2 random numbers, and we will use those random numbers as random seeds for our 2 random functions here. So it's like double randomized, and we are sure that it randomizes. Anyway, so the range here, it should have a domain as an input. A domain is actually it's a range. This is very misleading because the Grasshopper is not strict with naming, because there's something called a range, and it's a completely different thing. But a domain is a range of numbers, and it defines values between these 2 numbers. So if I put a range here, it actually generates 2 random numbers between something and something. And instead of just defining a domain here, I defined a number. And the thing that the Grasshopper does, it automatically converts one data type to another. So now it's converting the number into the domain. And that happens so that the number that I specify is the end of the domain. And by default, the start of the domain is 0. So now this is picking 2 random numbers between 0 and 1 million. We've got 2 numbers between 0 and 1 million, and they are used as random seed. And in each repetition, the number will be different. The random seed will be different. Okay. All right, I will save. And before I run the Anemone, I will save. We'll put it slightly lower, and let's set this to 50 repetitions, and let's see what happens. I think we should be done here. It should actually work. And you see it actually does. And it starts weaving the bird's nest, just like expected. And can you actually guess, I will set this to 500 repetitions. Can you guess what actually will be happening formally? Like what will be the tricky part here? Like what problem will we very soon have? Can you guess? And the answer was my computer will crash. No, this is a very powerful computer. No, it will not crash. But that's a good remark, certainly. So now we have almost 500 repetitions, and it visually doesn't change much. Now we've got 500 repetitions. The problem here is that it's basically just making everything more and more dense, because you create one line here, and there's a good chance it will be used for as a base for another line. So a new line will be created very close to that one, and then a new line will be created over there. So it's self-densening. So where it is already dense, there is a high chance that you will pick another line from that dense area, and it will make it even more dense. So it's like when there is a gravity somewhere and it attracts other objects, the gravity only increases. So it's like a snowball effect. It's packing more and more lines onto the same into the same position. And you see that, for example, this curve was only used several times. Like I can see 1, 2, 3, 4, 5, 6 times, 7 times maybe. Maybe all the other ones were used only 7 times, but it actually creates something that is, well, it's just getting more and more dense. We can maybe somehow fix that. I can think of some strategies, but I think just to prove a concept, this should be enough. This shows you that this is something that you wouldn't be able to achieve without using Anemone or any sort of looping algorithm. Let's just think a little bit how to actually achieve this, how to achieve like a more evenly distributed result. I will have a sip of water meanwhile. All right, here I am back. Do you have any idea how to make this a little bit more even? So one thing we can do is that we will Yeah. Okay, that's a very good suggestion. Defining more points on the curves. Yeah, that comes from the chat. That's a very smart option. We can actually define more than 2. We can, first of all, we can pick more than 2 curves, and then we can pick more than 2 points on those curves, and then select something that is the best fit for the problem. That's one option. Another option is it's a good one, and let's think about it. It will make things more complicated. Another option is that we can generate a new curve, but before we add it to the existing collection, we just think a little, like evaluate whether it's it adds to a more even distribution, or if it makes things more dense. If it makes things more dense, then we will not use it at all. We'll just drop it, and we'll dump it, and then we'll create a new one as a candidate, and so on and so on. So instead of creating more lines in one iteration, we'll still keep creating just one, and then make some sort of evaluation whether it's a good idea to add that line or not. Now, the thing is, what should be the criteria? I will just change the number of repetitions to only 5, and let's see what happens after 5 repetitions. You see that this is already quite dense. The problem is that if we only create one, no, if we create more in one step, then we've got we can choose the best one out of those, which is some sort of a relative evaluation. Whereas if we only create one, we need to have some absolute measures how to decide if we keep it or not. So there is a good and a bad part. So maybe creating more of them at once is not such a bad idea after all. Anyway. But how do we actually measure? I suggest that we divide the curve. We create a couple of points on the curve. So for example, let's make 10 points on the curve. Now let's pull the points to the existing lines. So we created this new line. We pulled we divided the curve so that we created 10 points on the line, evenly distributed. Pull point actually takes a point and brings it, puts it on the closest existing geometry. I'm pulling it to the previous set of curves, not including the new one, everything except the new one, which is here. I pulled it here, and it tells me the distance, how far did it actually pull all those points. And I will use mass addition. And this gives me mass addition takes a list of numbers and adds one to another. So if we've got 11 numbers here, so this is an addition of all of them. So the result will be a sum of all distances, where how far they have to travel to actually stick to an existing geometry. The thing is that if this number is really low, it means that the line is really close to other existing lines. And this one, visually, we can see that it's super close to this one and also this one and so on. So maybe what Gizem was suggesting, like defining more points on the curves, that's a very good idea eventually. So let's generate in each iteration, let's generate more than one line. Let's generate more of them. And then pick the one that has the sum of the distances largest of all, which means it's the one that is far away from the rest of the geometry. So it will make the whole structure dense more evenly. Is that clear what we are going to do? Okay, so so my suggestion then is okay. So my suggestion is we need to create more curves, more straight lines here. So instead of let's just copy this. Let's just make a new version of the whole thing. Sorry, like this, because I'm going to change it a lot. This will be much slower, but also it might be a little bit easier to understand. So instead of just picking two lines, two curves, and picking two random points, let's just generate a lot of random points on a lot of random curves. So let's just say that we want to have 20, we want to draw 10 random lines connecting the existing curves. I will delete everything and I will just keep copying it back from up there if I need it. So basically, okay. So this is the collection of curves. Now let's pick one of them. So from the list, let's pick a random one. So this list item picks one item from a list. I need to specify its index. So let's generate random index based on list length. So I will generate a random number between 0 and a number of elements that I have. So in my case, it's going to be number 2. I can convert it into integer, which basically will floor the number. So I selected line number 2. And then I need to also select a random point on that curve before I even had the reparameterize component here. This is quite important. So reparameterize, and then I also need to generate random number between 0 and 1, and I will evaluate the curve. So I will evaluate a random curve and a random parameter, right? And I want to generate 20 points like this, because I want to generate 10 lines. So if I want to have 20, then let's say 20. Let's generate 20 random integer indices. So this selects 20 random lines. I know there are only 3, but some of them can repeat. So so the first random point will be on line number 2. The second one will be on line number 0, then 0, 3. Oh, there is no 3, so I need to change this to -1. This actually works because this is wrapping around, but to be completely correct, I need to generate a random number between 0 and 2. So it is a random number between 0 and length -1. Okay, so the random points are going to be on 2, 1, 0, 2, 0, 1, 2, 1, 0, and so on. And also there are random parameters here like this. So it actually generated, yeah, these random points. All right, and then the thing is that if the 2 points are on the same line, then I will just generate a new line as a segment of an existing line, and I don't want that. I don't want the 2 numbers to be on the same line. So let's resolve that later. Now I've got 20 points, and I need to draw 10 lines between those 20 points. So I will do weave. It's been years since I last used, it's not weave, is it? Not weave, it's the other one. It's dispatch. Dispatch, is it? Right? So yeah, I think so. So dispatch pattern is going to be true, false. I will explain what am I doing here. I just need to be sure that it actually works. I haven't been doing this for a long time. Okay, so dispatch takes a list, and you can use some pattern, and it dispatches or picks the items from a list and puts it to list A or to list B based on the pattern. So, and the pattern repeats. And list A is when the pattern is true, the item goes to list A. When the pattern is false, the item goes to list B, and this keeps repeating. So if I've got 20 points here, it's going to be called true, false, true, false, true, false. So it means that every second goes to every odd goes to list A, every even goes to list B. I hope this is kind of clear. Now, when I draw a line between these 2 lists, then actually I create 10 different lines. But the thing is that it might happen that the 2 points are on the same curve. Like if this is a straight line, if the curve is a straight line, then it would be undistinguishable from the existing curve. So I don't want to use lines that come from the same curve. I will easily check it this way. So I will dispatch one more time, but this time they will be only these integer numbers, which are the indices, the random indices that I picked. And if you look inside, it tells me that from which line, from which curve comes the first point, and from which curve comes the second point. And if they are the same number, then I don't want that, because that means that that will be just connecting 2 points of the same curve, and that obviously happens for line number 7. So if this is, if I want every 3 point go to list B and other 2 go to list A, what can I do? Okay. So you can change the pattern to something like this, true, true, false, and this will be repeated over and over again. Actually, I used a panel and I switched off the multi-line data so that this actually works. I don't know if you're aware of that. You can have a panel and you can put some data here. And this, by default, it allows multi-line data, which means one piece of data can be in multiple lines. So eventually, this is just one piece of data, even though it's a couple of lines. So that's one piece of data. If I switch off the multi-line data, so it's by default it's on. If I switch it off, then every line is a new piece of data. So now I've got 4 pieces of data. So that's what I had to do here. I had to say this is a panel. I said true, false. Now this would be one piece of data. When I switch this off, it's 2 pieces of data. And now I've got twice true and then false, and this keeps repeating. And if you see, if you look here, this has got 14 values and this only has 6 values. But anyway, this is not what we want for the moment. Like this. Okay, so now I want to compare these indices. If the index in the list A is equal to list B, then I want to remove that line because that's not fit. So if the number here equals number here, and that will give me another pattern, and I'm asking about inequality. So if they are unequal, then everything is good. So unequal, true, unequal, true, true, true. Number 4 is not unequal, it's false. And number 7 is not unequal. And there is a component called cull pattern. And cull basically removes everything that in the pattern is false and keeps everything that in pattern is true. So eventually I should have 8 lines here because 2 of them were removed because the pattern was false. So now I'm sure that these are not connecting points of the same curve. That's good. And also now I have this pull thing here, that the pull logic that I had here. There is also this. So I said I will copy out the values from here. So I will put a curve here like this, and then like this. Okay, so what am I doing? I'm taking all the new lines that I created. These are good candidates for a new line to be added. Now I divided all of them into 10 points, actually 11 points. Now I'm pulling all the 11 points of each of the curves to the existing geometry, not the new one. And then I'm calculating an overall distance where it had to be pulled. And I'm interested in the one that has to be pulled the furthest away. So let's have a look here. It gives me numbers, and it's in a data tree. I can flatten the data tree. The data tree happened here because when you divide the curve into points, you've got one curve at the beginning, and then you create 10 points. So from one item, you create a list. But if you have a list of curves, you need to create a list of lists. So that creates a data tree. But eventually, we also simplified the data tree so that in each branch, there is just one value. So we can easily as well flatten. So now we have a flat list again. Here, we have a flat list of lines. And let's sort this list of distances. This is the key for sorting. And let's, in the same fashion, let's sort the lines. So it's like in an Excel spreadsheet, you are sorting according to one column, and also the second column sorts. So here I'm sorting the distances. So now the distances are from the smallest to the largest, but in the same fashion also the lines are sorted. But I'm actually interested in the longest distance that the points had to travel. So I'm picking the one list item from the list of curves that is the last one, which is index -1. So it's this one, and let's see it. It's the curve, it's this one. So this one had to travel the largest distance. And because of that, this is the best candidate to be added. So now we can add this one to the existing list of curves. So it's this one, and the other ones, we are going to dump them. We don't need them. I will just hide everything. And this was the best candidate that we could have. So now we've got 4 lines, and we added the one that created the most homogeneous result. Also, let's have a look here. Just creating some sort of random numbers here. So yeah, I've got two randoms here, and I need to make sure that in each iteration, each repetition, a new random number is being selected. So again, I will take the random, like double randomness here, like that, and let's enable it. I will put the counter here as the random seed. I'm creating two numbers. One is a seed for here, one is a seed for here, like that. And that should be it. And now let's give it a try. I will do it like that. And you see that it generated random lines here. And it seems a bit more diversified than it was before. Let's do the 500 repetitions. I saved just to be safe. Let's do the 500 repetitions, and you see that it actually seems like it was a good logic. You see, it's not so dense in one place, and it always prefers the one line that actually is the furthest away from all the other lines. Still, there is some density in the middle, but nevertheless, I think the result is kind of working for me. So is this logic clear? Okay, so this is something that that brings some sort of unexpected result, even though you know exactly what the logic behind is. I know it's a very simple notion, but still, this is something that you wouldn't be able to just draft in a simple way. Of course, you just can keep drawing lines, but eventually you can do a lot of things with this. One great thing about the whole thing that we made here is that we were able to evaluate which one to add because we already had the data. So the logic that we used. For creating the lines, it already contained a lot of information, and based on that information, we could have done some evaluation, which is pulling the points to all the geometry and selecting the most fit one. And that's already something that you cannot do without the use of computers. You cannot evaluate things when you don't have the data, and we do have the data only thanks to the fact that we created the shape based on the data. So anyway, in the schedule, there is still one more thing that we are supposed to do, and that's the swarms. To be honest, we need to finish in 15 minutes. So this took much longer than I expected. So I've got a suggestion. And also I have to admit that I'm kind of tired speaking the entire day, and I believe so you are. So are you. The question is, but how can we change these curves into a B-rep? So what I've done in the rendering here is that I just made a pipe out of the curves. So I just wrapped a pipe around. That's one possibility, which is when you are done with a repetition, then you can make a pipe, but just beware that the original pipe from Grasshopper is a very, very slow component. So the NURBS pipe is super slow. I will save, and it may crash my computer, but there is a mesh pipe coming from not really Lunchbox, but some toolbox, there is a mesh pipe component. There is one also in the pufferfish, but yeah, we can use that one. I usually don't use pufferfish, but I have installed it recently because I had to use it. But let's use the mesh version, which is for rendering. It doesn't really matter, but this will be too slow. So let's hope that this one is fast enough. So this is it took 1 second on my computer, which already is a bad sign. So now you can actually create geometry out of that. So it's got some thickness. Another option, Weaverbird doesn't really help you. Well, Weaverbird doesn't contain the mesh pipe, and the Weaverbird doesn't really help you here much, because you can just smoothen the things and so on. But what you can do is you can use Cocoon or any other voxelizing algorithm. There are many. I think I don't really have any installed. There is one. Where is it coming from? Pufferfish. Anyway, you can voxelize it, or you can do marching cubes. There is a great component made by David Stasiuk. I always just look it up like this. Marching cubes is an algorithm that basically takes voxels. Voxels are spatial pixels. So you divide the space into cubes, and that's let's see. Let's see the voxels. Yeah, this is a good example. So you basically divide a space into discrete boxes, and you can convert any geometry into voxels. Basically, if you have any geometry in the space, and if you divide the space into a cubic grid, if any geometry is inside of the grid, then the cube exists there. Otherwise, it's empty. So you can see it here. Basically, these are voxels. You can convert any geometry into voxels very easily, and it's some sort of a brute force approach to creating volumes from some other input data, and it's actually very useful. And when you have the voxels, when you already know that there should be a voxel in the space somewhere, you can do some advanced stuff, which is called marching cubes. That's only an algorithm that instead of just making, you can think of a two-dimensional approach. So this would be a voxel because there is something. So it would be like this, like angular, like this. Chop, 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 chop. But instead, marching cubes, it actually creates some sort of a smoother result. So you can see, for example, I don't know, here, that instead of having just cubes, it's a bit more angular. And I would actually like to see some comparison between voxels and marching cubes. Let's see. Yeah, here. The one on the left, or even in the one on the left are voxels, so they are cubic, and the one in the middle are marching cubes, so they are much more smoother. And when you smoothen them out, that's completely smooth. I will actually show you the stuff during the last day. We made our own software, and it's using voxels and marching cubes a lot. So we kind of use that a lot, and I can explain much more in depth. The reason why I'm showing you now is that you can take this marching cubes algorithm by David Stasiuk. This is already 6 years old, so I believe there is some newer version. Maybe that's the Cocoon plugin or something like that. But that's just one simple thing that. Wait, it probably opened a new Rhino for me. Anyway, in the downloads, I can open this. There is just one C# component that he made, and it actually converts any set of points with some charges into a smooth mesh geometry with marching cubes. But I'm worried that this will be very slow to convert to marching cubes, which is actually quite strange to me, because maybe because the software that we made, the marching cubes there are incredibly fast. So I think, well, it's either more sophisticated or it's doing something that I don't understand really well, but it's quite useful here. And maybe also the voxels in pufferfish, I'm not sure. As I said, I'm not really using it so much, but you see it crashed my computer right now. So anyway, that's how you can generate some volumetric output, and it would look something like this, I suppose, or maybe even something like this. Good. All understandable? I somehow need to restore my computer now. It's actually running Rhino twice because I randomly opened the marching cubes twice, and both of them are now stuck. So anyway, my suggestion was that for those of you who are uh, yeah, somebody's commenting on YouTube. I will read it. More efficient way would be to compare the distance between the random generated points to the length of the initial curves as a condition for creating a new line. Which means, you think so? If I compare distance, which means the length of the newly created line to the length of the initial curves, so it basically prefers the longest of the curves. That means that it would favor the ones that are most on the outsides of. I don't think that actually that suggestion works, or maybe I don't understand. I'm sorry. Maybe you're right, but I just don't really get it. Anyway, let's go back. I promised to you that I will teach you also how to do swarming and how to do flocking behavior. We don't really have time, and I don't really have energy left, but I don't want you to miss out. So for those of you who subscribed as an active participants of this workshop, I suggest that I will send you a free access to the tutorials that I made on that topic, which is here in the research Grasshopper sessions, and that's flocking 1, flocking 2 that I recorded some time ago, and you will see basically how to create these things, this one and this one. So I will send you links to actually download these for free. You will find it in your email, and basically that's I don't know, that's 4 hours of tutorials. We don't really have 4 hours left. And that's kind of accurate. That's an in-depth insight to that. Is that okay for you? Is that something that you can live with? The tutorials will be available like forever, so you don't have to watch it now or something. All right then. Do you have any questions? Is there anything that you would like to tell me, or? I'm actually also taking complaints. If you don't like something, just let me know. We still have 5 more days ahead. That will be a marathon. Just let me know if anything it should be different than it is now. Just let me know. Okay. So it seems like everything was clear. There is also a new. Well, thanks for the. Yeah. I hope that it brought you some new perspective on the computational design. Yeah. Okay. Maybe somebody will have a question when you go through it yourself. Well, I will send you all these files, and also in the email I will send you a link to register for the free tutorials. Still, there is a comment on YouTube from Matouš. Who suggested to compare the length. He said it would require more loops, but without creating an unnecessary geometry. Yeah, that was what I suggested before, just creating one piece at a time. But yeah, I still don't know if comparison between like finding the longest possible. I don't know. Maybe you're right. I would just have to see what your suggestion is. If you have time, then please just make a definition. Send me the definition, and we can have a look and discuss tomorrow. Yeah. Okay. So thank you again for watching. It's been 2 hours now. I will edit the videos